All right. Can they see this? When you get into class, you will get one of these. Okay. All right. I want you to find your inner child and fly your plane. So go ahead.
Look, we don't even need the sounds. We could just have the air conditioning.
True.
All right. Some of you are finding your inner child very well. Some of you are.
Oh, this plane flies backwards.
I'm just enjoying it.
Alright, so it turns out, I wanted to see, this is actually an experiment. I can put you all in the science fair. I wanted to see if you would do it quietly, you know, or you would make a sound. I heard several sounds. And some other. So, it's kind of funny because I heard not many, some do, but not many, take a plane when they're playing with it and go, nee.
That plane goes, nee.
They don't. What do they do? They go, nee. And that's what I heard. And so it seems like even like a 2-year-old, maybe even younger, knows about what we're going to teach today. And that's called the Doppler Effect. Heard of it?
Jump, jump, jump.
Right, and a plane.
Oh, I love that.
The Doppler Effect.
It's like, wow, wow.
And the eraser is my gift to you.
Aw, I will treasure it forever.
Yeah, I don't think so. It makes it to the end of the week, it'll be amazing.
And Keen uses all of the erasers. Oh, we just said her.
I just said her name. I'm just here for me, like I can throw that in.
Alright. Having heard about the Doppler effect, if I careen you all out to the parking lot and I drive by in a car and I beat my horn, what you hear is me as I go by. And the train whistle is and the plane. So all these different things are examples of the Doppler effect. What is changing? What is changing? We learned a little bit about characteristics of sound. What's changing when you fly? What in your ear, to your ear, what's changing, MD?
Amplitude?
Not, yes, but what feature does amplitude? Amplitude was volume, so it wasn't that. But what characteristic hitting your ear was changing? It wasn't the volume. So it's all the same volume. What's changing? What's that called? MM?
Is it just frequency or is it?
It is, but what does frequency relate to? Frequency causes a change in what? Not volume. What's the other thing? What's different between, Alex, what's different between, what's the difference there? It's not volume. What's changing?
Oh.
MM?
Isn't it pitch?
Yeah, pitch. Alright, so let's define that, the Doppler effect.
So
Change in pitch, related to sound emitted from moving objects. So, I'll define it like that. You know what I mean. What I mean is, how do you write that on a page? So, I'm not sure. So, that's the best I can do. When I write that, I already see there's some error in it because the sound doesn't have to be moving. You could be the one moving. It works the same way.
But don't you have to move really fast for it to like make a
Not really,
difference?
like say if there is a factory and the end of day whistle blows and you're in a car or even a bike moving toward it, you will also experience the Doppler effect. Alright, so let's see why this happens. if you would, draw, we'll work on we'll say we're in a car. They're fairly, the cars I am in are very easy to draw. A smart car. And let's say the horn is applied and the sound waves ripple out from it like a stone hitting a lake. So these are the waves. The purple parts that I draw are the crests. They wouldn't have to be. I could call them the troughs or any point in between. Let's just say these are the crests that are emitted out from the horn being applied. If you are still, and the car's coming towards you, you will hear the horn. If the car is still and you are still, when the waves hit you, they will pass like that, and you will hear an even pitch. You'd hear beep. That's what you'd hear if the car was still and you were still. So do a little sketch-a-roo. But normally, if the car's horn is being applied, normally it's not still. It has some motion involved. So here's what we're going to draw next. This time the car is moving, and as it moves, here's what happens. I will apply the horn. Are you up with me in your sketching? Second sketch. So we're starting again, either above or beside. I mean below or beside. So the first ripple comes off of the horn. The first crests emit in all directions. But then the car, what have we been doing all period? Talking about church, I guess. All right. As the car goes forward, what happens? Well, this ripple has already been emitted, but the car is going to go forward and emit the second one. So it's going to move to here. Kind of hard to draw. I'll just leave the car there and say it was back here. So here's where it was in the back. So now it's going to keep emitting, and as it does that, it's going to be catching up to the wave of the emission that it already made. So as it goes forward, here's what happens. Here's what happens. As it goes forward into these crests, it's catching up with the old ones and emitting new ones. So what happens? So I'm going to actually write that in words. Car catches up with old I'll say, previous old crests, and creates and continues to create new crests. Alright, so therefore it looks like this. So we see a bunching of crests ahead, and what happens behind, we have spreading out of the crests behind. Alright, so have a sketch of that with those words surrounding it, and we'll discuss what that does to our ears. And I'll give you the formula before the bell rings so you can rest in peace tonight. So now you're standing here on the side. You're not going to be hit by this car because he blew his horn. So anyway, so what happens is you're getting all of these crests now that are bunched together, which is exactly like frequency is rising. We have higher frequency, you have higher pitch. So the horn is still, it's kind of interesting, the horn is still emitting at the same old but you are hearing it because of this bunching as higher than it is emitting. So that's quite interesting. And if you were standing behind, you would hear the pitch lower than he was emitting. So it's quite interesting phenomenon. The Doppler effect is its name. Here is the equation, and that's probably all we'll have time for today. The frequency observed, that's what you hear. Frequency observed. And I'm going to need more room, so start over here. Frequency observed, that's what you hear, equals some fraction times the true frequency, frequency true. So if they're both still, if you are still and the car is still, these will be equal. But if there's the moving involved, then this is going to be a fraction, which will have a numerator and a denominator. If you are in front of it, then you're going to hear a higher frequency, so you expect a fraction in here that's greater than 1. If you are behind it, you are going to hear lower frequency, so you expect this fraction to be less than 1. So if you would just write it down, and we'll investigate it and do problems tomorrow. Velocity of the sound plus or minus velocity of the observer is the numerator. On the bottom, velocity of the sound plus or minus velocity of the source. All right, get that down and you are excused. Goodbye.